Hello, everyone. Today we will be presenting Modulo Continuo, 5-axis ceramic additive manufacturing applications for evaporative cooling facade modules. My name is Amelia, and together with George, Dongyun, Devashree, Hyejun, Zach, we from the Harvard Graduate School of Design will be presenting this project. Recent developments in industrial robotics present an increasing degree of control in additive manufacturing, enabling customization of architectural building components at the scale of the individual unit. Combining the affordances of a 6-axis robotic arm, paste-based extrusion, and terracotta clay, Modulo Continuo asks, how does 5-axis additive manufacturing afford part customization in a modular ceramic system utilizing evaporative cooling principles? The design of the facade modules is developed concurrently on 2 scales. First, at the scale of the tectonic unit, as a self-supporting, interlocking modular system of curved modules with an embedded water reservoir for evaporative cooling. Second, at the scale of the toolpath, in which the density of the infill geometry in the modules is calibrated based on the principles of evaporative cooling. This research presents opportunities for visual and performative part customization of the infill density and patterning of the modules based on different evaporative cooling requirements. In recent years, the architectural research community has developed a range of additive manufacturing paste-based extrusion applications in architectural design. The breadth of these ranges from small-scale multi-material printing with customized extruders to large installations and intricate porous screen systems. The research began with the development of several module systems that simultaneously interlock and self-support while producing an illusion of surface continuity through weaving operations.
Through the combination of the module design and evaporative cooling principles, the facade comes together as an interlocking system with continuous water channels embedded within the part geometry. The design draws on the hypothesis that capillary action or gravitational pull would wick the water through the infills on bisque ceramics. A gradient of densities was explored for infill types A and B. The more intricate dense patterns have greater surface area and consequently produce greater cooling effects. Each infill pattern facilitates evaporative cooling through capillary action. When air flows across the moistened, unglazed ceramic porous pattern, it produces a cooling effect. The end result of the modules that were printed was a combination of the difference in infill pattern designs, as well as the varying robot speed and extruder pressures. From the design phase, the geometry of the module and the infill pattern are determined and are consolidated in the computational workflow. Each module was contoured along its isocurve, and the infill patterns are consequently mapped onto a contoured plane directly. Projected infill patterns were generated in separate workflows, which created the production of these different infill types and density variables. From this workflow, the final toolpath geometry of perpendicular planes was generated computationally using the plugin Machina in Grasshopper and simulated in Robot Studio before fabrication. Print samples were produced using a 6-axis ABB IRB 4400 robot equipped with a commercially available extruder system produced by Potterbot and a low-fire terracotta clay. These were first tested on flat geometries. And then we transitioned to flat infill patterns, which had more of a type of topological variations. So doubly curved foam substrates were consequently utilized. Early tests with this IRB robot revealed that the drying of these prints was better suited to a concave, so that it's dipped substrate, instead of a convex, the hump substrate.
The end results of the modules that were printed was a combination of difference in infill pattern designs, as well as the varying robot speed and extruder pressure. When the robot printing speed was fast, the thickness of the printed clay became too thin, causing structural weakness. And when it was too slow, visual porosity disappeared. Since there were physical factors that could not be consistent, such as the quality of the surface and the viscosity of the clay, the robot's speed and the extruder pressure were adjusted according to the situation that while printing each module. 2 modules were submerged in half an inch of water, and the water accession rate was noted after 3 hours. Module 1 was designed as per Type A Infill 2 with a visual porosity of about 54%, and Module 2 was designed as per the logic of Type B Infill 4 with about 28% visual porosity. The distance between the 2 rows in case of the Module 2 was significant, preventing it from behaving as a continuous porous mesh, and hence having less evaporative cooling effect. The capillary action in Module 1 was more uniform, versus Module 2, the accession was not only through the vertically connected borders and not from the central core. The presented research allows for a customization of visual porosity and of surface area for each module, proposing for the possibility of a highly tunable wall or facade. With calibrated infill density, the porosity of the modular wall can be adjusted according to specific programmatic needs. This diagram shows the subdivision of a curvilinear surface. By discretizing the plane according to a predetermined module size, gradients of pattern infill densities were generated from dense to sparse. Modulo Continuo builds upon the recent advancements of additive manufacturing technologies. This project addresses the current limitations in creating complex geometries through an integrated workflow, from the individual ceramic module to a performative evaporative cooling facade. The combination of an aesthetic and performative evaporative cooling properties make it suitable as a self-supporting single or double skin building facades in hotter climates. Further investigations will address the directionality of the infill pattern to optimize vertical water absorption, improving clay-based printing accuracy and the exploration of new geometries for a robust stacking assembly logic. This would ultimately lead to a more robust calibration of infill percentage to evaporative cooling rate.
That's all from Modulo Continuo. Thank you.